So let's first take a look at hypothesis testing, where we're going to test a population mean. And much of this will be very similar to the confidence interval that we developed in a previous module. So there are times that we want to see if a sample that we have matches a general population. So we're looking for, say, take the temperature of a group of students. The average temperature should be 98.6, and obviously it's going to be slightly off, but we want to test to see if this sample mean is different from the population mean. Another example might be take a salary of a department of 50 people and see if the average salary in the department is the same as the overall salary of the corporation, 2,000 people. And then we want to take a sample of GMAT scores for a given school and see if it matches the population of GMAT scores across the nation. So these are some examples of where we might test a sample mean to a given population mean. So in order to determine if a sample mean is statistically similar to a population mean, we need to really understand what's happening. First is we have to assume that the sample is normally distributed or somewhat close. Let's see why. If we know that there's a population distribution that is normal, with a mean of 98.6, as we can see here on this graph, then any sample that we have should look something like it. And the mean of the sample shouldn't be too far away from the population mean. When we take a sample and we find that our sample looks normal, has a mean of 99.1 with a standard deviation of 1.1, graphing it will look close. Now, we have a statistical measure, the t-test, which will measure how close the sample distribution is to the population distribution and tell us whether they are statistically the same, whether the sample matches the population. So let's see how to do this. So the first thing we need to know is how to set up our hypothesis test. So let's take this example. We conduct a sample of temperatures of students, and the sample has 30 students with an average temperature of 99.1 and a standard deviation of 1.31. We then calculate our t-statistic using the formula to the right. And so here we have our t equals x bar, which is our sample mean, minus mu, our population, or what would be our expected population mean, divided by the sample standard deviation, which is divided by the square root of n, the number of observations. So this formula should look familiar because we used this formula when we developed our confidence interval a few modules ago. So what we're going to do first is we're going to put the variables that we know. We have our mu0, which is going to be considered the population mean. So you might hear some people say mu0 or mu0 or just mu, and that would refer to the population mean. And this would be 98.6. So this is what we're testing against. X bar is our sample mean, which is 99.1, and this is what we got as our average from the sample. Our standard deviation from that sample was 1.31, and the number of observations that we have is 30. So all of this information is either given to you or you calculated from the sample that you're given. What we're going to do is we're going to create our hypothesis test, and our hypothesis test will always look like this. There's two parts to it. We have an H0, which again is our null hypothesis, and this is what the current belief is. So in this case, our belief is that X bar is equal to 98.6. And then we have the alternative hypothesis, which is what we're testing for. And we're basically saying that the alternative hypothesis is that the sample mean is not equal to 98.6. Now, statistically speaking, there's going to be some threshold, so it could be 98.61, and that might be the same as 98.6, or 98.54, and that might be the same. And again, that has to do with our confidence level and ultimately the standard deviation. The t statistic is actually going to handle that for us. So even though our sample here clearly looks different, 99.1 against the 98.6, is it really that far off, or is it just a small random probability that your sample mean was just slightly off from the true mean of 98.6? And that's ultimately what we're looking for. So again, we have our two pieces to the hypothesis test. In all cases, it will be an H0, an H0 or a null hypothesis, as well as an alternative hypothesis, HA. The H0 is that X bar is 98.6, as it should be, and the HA is equal to X bar not equal to 98.6. So when we plug in our numbers for the calculation, we have t equals 99.1, which was our sample mean, minus 98.6, which should be our expected population mean, divided by 1.31, which is divided by the square root of 30. And this gives us a value of 2.07. What we'll do is we will put into Excel, now remember, because this is a t-statistic, we're going to be using the t distribution, t.dist.2t, because this is a two-tailed distribution, because again, the equal sign, we're looking for things on the left or on the right of the mean, is going to be, so that's going to give us a two-tailed distribution. We put in our 2.07 from the t-statistic, and 29 refers to the degrees of freedom. Recall that the degrees of freedom is equal to n minus 1, the number of observations minus 1. When we do that, we get a t-statistic of 0.0476. So how we test this is this. Since our p-value, which is what it's giving us, is 0.0476, and it's less than our 0.05 confidence interval, we can reject H0, or the null hypothesis, and state that the sample mean is different from the population mean. It's important to know that when we do these tests, we're never accepting the alternative hypothesis. We will only do one of two things. Either we will reject or we will not reject the null hypothesis. So in this case, because the p-value that we obtained from the Excel function, which is 0.0476, is less than 0.05, we can reject the null hypothesis and state that the sample mean is different from the population mean. So this sample was somewhat different than the population. Now, for a left tail hypothesis test, as you could see here in the middle, we have our null hypothesis that x bar is greater than or equal to 98.6, and our alternative hypothesis, x bar is less than 98.6. So that less than sign there means we're going to have a left tail. We calculate our t-statistic in the same way we had before. It doesn't change, and we end up with 2.07. But this time, we're going to have 1 minus the t-distribution.rt, t-dist.rt, 2.07 with 29 degrees of freedom, and we will end up with a value of 0.977. Now remember that since 0.977 is greater than 0.05, we cannot reject the null hypothesis, and therefore we cannot state that the sample mean is not less than the population mean. It is definitely the null hypothesis that is stating that it is greater than or equal to 98.6.